In this lecture, we're going to discuss the word problem for commutative groups. So what is the word problem? The word problem in combinatorial group theory is to determine whether two groups are isomorphic from their presentations. Combinatorial group theory, as we remarked, is when you describe a group through generators and relations. So a presentation is a way of describing a group by using something called generators, the elements that allow you to express every other element as a product. And then the other thing is you call the relations between the generators. We call that a presentation of a group. And combinatorial group theory is all about describing groups using presentations. And the main problem in combinatorial group theory, there's other related problems, but this is sort of the most important one, is let's say I give you two groups. I give you a group, I call it G1, and I say this group has three generators, and x cubed is 1, y squared is 1, and then I say z cubed is xy to the fourth, and then I say something like y cubed is z squared xy. Well, let's say this. I give you this group, and then I give you another group, let's say G2, with, let's say, two generators, and then I say something like AB squared is 1, and so on. Let's say this. Let's just say that. And I ask you, is G1 isomorphic to G2? Are these really the same groups in disguise, but they just are presented very differently? And at first you might say, well, you have three generators here, you have two generators there, but that does not really matter. You also have a lot of relations here, and here you just have one relation. But again, it does not really matter. You can have two presentations that are radically different, but in the end, they describe the same group. We saw an example actually last time, a fairly simple example, where we had two generators and three relations, but in the end, you could have simplified it to just one generator and one relation. So just because they look different does not actually mean they are fundamentally different as groups. They might be isomorphic. And this is what we call the word problem, because if you look at these, this is sort of like words. This is like your alphabet, and these are the grammar for the alphabet. These are like the rules that the alphabet satisfies. So we call it the word problem in group theory. And as we remarked, there is no general purpose algorithm that will solve a problem for you like this. Now, in some special cases, in some special class of problems, you might be able to do it. And I should say this is actually a very active area of mathematical research. Like, this is something that people actively work on nowadays in group theory. And what I wanted to discuss today is the word problem. There's an algorithm, so there's a method. So there is a method for understanding the group in the commutative case, or the abelian case, if you want to say that. So if the group happens to be a commutative group, there's actually a systematic method for doing it. And interestingly, it uses linear algebra. So let's make some definitions and show you how this works. So let's make a definition. So we say that G is a finitely generated abelian group if and only if, well, we know what an abelian group is. That's not the problem. So we want to say what it means to be finitely generated if and only if we can find a collection of elements in G so that every element, every x in G, can be written as a, now usually we say product, that's what we said last time, but the convention is that if you're working in a group in general and you do not know if it is commutative or not, then you use a product. So then you would write A times B, where the multiplication symbol is the binary operation here. But if you're working in a commutative group, then the convention is to use a sum. So instead of writing a times b, you would write a plus b. And instead of saying, let's say, a squared, you would write 2a, because you're just adding a twice. So in a group in general, when you write a cubed ba, that would mean a, b, a. And you're not allowed to move the a over to the other side, because in general, it's not commutative. But in a commutative group, you would rather write, so you would write this as a plus b plus a. And because the group is commutative, you can put the a in front. So it makes sense why we use the addition notation. And then we would write 3a plus b. So that's the way we would write it. So that's why we're suddenly using sums. It's just a convention. So we can write it as a sum. It's coefficients. So a1x1 plus a2x2 plus a(n)xn, where the coefficients are integers. Okay, those are integer coefficients. The reason why they're integer coefficients is because if this is, let's say, 3x1, then you're just saying that x can be written as a sum of 3 choices of this generator. And if it's a negative number, if you have, let's say, negative 2x2, then that means you're adding 2 inverses of x2. That's what that would mean. So the negative is just the inverse in the group. So this actually looks quite nice, because this is basically like a linear combination. This is what you call an integral linear combination. Integral in the sense that the coefficients are integers. It's not exactly like linear algebra where the coefficients are real numbers. These are integers, but it's very similar to that. And in fact, this should remind you, so this definition should remind you of what you call a spanning set for a vector space. But when you have a vector space, you talk about a spanning set, a set of vectors that allow you to express every other vectors. But you do have to be careful, and this is the part where you have to be careful with. So just be careful that x1, x2 up to xn do not necessarily form a basis for G. To form a basis, it would mean that every element in G can be written uniquely as a combination of these. And also, it is conceivable that G has no basis. You cannot necessarily find a basis. We gave an example last time. So if you look at the group of integers mod 2, there is no basis, because every element will satisfy the property that, so if x is an element of the group, then 2x will always be 0. So you always have that relation. So in the basis, you have no relations. If this formed the basis, there would be no relationships that existed between x1 to xn. So that's the definition of what it means to be finitely generated. There's a finite set of, to abuse terminology, vectors, but technically they're elements of the group that allow you to express every other element. And the main theorem that I want to mention here, and some of you have possibly seen this theorem in an algebra course. This is sort of like the main theorem, that if G is a finitely generated abelian group, then G is isomorphic to a product of Z's. Okay, so here's an example of an abelian group that's finitely generated. That would be Z. This group is generated by the number 1, because as you keep on adding the number 1, you will generate every single integer in this group. Also, this is a basis for that group, because there's no relation on 1. No power of 1 will ever become 0. Well, by power, in this case, we mean no multiple of 1 will ever become 0 unless the multiple is 0 to start with, but then that's just a convention for the identity element. So this is what it means to be a finitely generated abelian group, is isomorphic to a product of z's and integers mod n. Okay, that's the, so for example, you can have G in the end, and it might look like this. You might have 3 copies of Z. Maybe you have Z mod 5Z, and then maybe you have Z mod 2Z. So that would be an example of how it looks like in the end. It's a product, it's a finite product, maybe we should say. A finite product of those. So the group is isomorphic to this kind of product. So this is like a classification theorem for groups, for abelian groups. Such a classification theorem does not exist for groups in general, but it does exist for abelian groups. And fortunately, it's not really that difficult to prove. We'll be able to prove it today. We're not actually going to prove it directly. I'm going to show you the method to how you determine those factors. And then once you see the method, then you'll see why this theorem works in general. So then you'll understand why it works. Probably, if you've taken an algebra course, you've definitely seen this. And I want to add a uniqueness part to the theorem. So this is like the existence part. This is the existence. It says there exists a way to decompose G as a product of those. That's sort of like the actually easier part. You would think that's the harder part. The harder part is the uniqueness. So if you go back, it's a little bit reminiscent with what we did with the fundamental group of the circle. We argued that we had that the homotopy class of the loop that goes around one time is the generator loop for the entire fundamental group. And that was like the easier part of the argument. The harder part of the argument was to show that different powers of that generator are not homotopic to the constant loop. So in other words, it's like a basis. It's like a basis for the group. That was actually the harder part to show. So this is like the main theorem. The harder part is the uniqueness part. So I want to just make an observation. So I want you to note the following. Note. So if you take Z mod, let's say 15Z, this is actually isomorphic to Z mod 3Z times Z mod 5Z. So these are actually isomorphic to each other. This is basically what you call the Chinese remainder theorem. So if you've seen this before, it's just a quick reminder, because what you're saying is if you take a number mod 15, so if I tell you the remainder a number leaves mod 3 and the remainder it leaves mod 15 mod 5, then you're able to recover what the number was mod 15, because 15 factors as 3 times 5. So it's called the Chinese remainder theorem. So if you have Z mod 15, you can split it like this. Okay, you can split it. However, if you have Z mod 25, this is not isomorphic to Z mod 5Z times Z mod 5Z. I'm not going to tell you the reason why not, but you can think about it yourself. It's definitely discussed in an algebra class. It's not difficult. Just to give a very simple, quick explanation, because every element in this group, when you add it 5 times, it gives you 0. And every element in this group, when you add it 5 times, it gives you 0. So if you take anything, so let's say you think of this very concretely as a Cartesian product. So if you take anything in the Cartesian product and you add it 5 times, then both coordinates become the identity element. Whereas here, you can find elements that when you add them 5 times to themselves, they do not give you the identity element. So there's no isomorphism between this one and this one. So you can split it. So you can split it only in the case when the numbers have no common factors. So 3 and 5 have no common factors. Of course, other than 1, but that's kind of silly. Other than 1, you're allowed to factor it like this. Whereas 25, those are shared factors. So that's when you're allowed to do it. So there's a uniqueness theorem. So the uniqueness part, the uniqueness theorem would say that decomposing G as a product of the integers and integers mod nz is unique. There's only one way to do it. If we use z mod p to some power kz, where p is a prime, and k is an integer. So prime powers. So if you're using prime powers, it's kind of like prime factorization of a number. So like, for example, if you have z times z times z, let's say you have 3 copies, and then you have z mod 5z, and you have z mod, let's say, 5z, then this is not isomorphic. Let's say you have this. That will not be isomorphic to z mod 25z. Even though 5 times 5 is 25, that's what we mean. If you would not write that, okay? So you would split the factors into prime factors. Also, to maybe add this will not be isomorphic if you only had 2 copies of z. So here you have 3 copies of z. If you had 2 copies of z, and then you had this. So that's kind of like the uniqueness theorem, that there's only one way to do it. So again, this is something that is mentioned in an algebra course. The uniqueness theorem is a lot harder to prove. You have to sort of treat both cases. You have to treat the case where you have to argue that the number of z factors is unique. So you cannot have one decomposition where you have 6 z factors and another one that has 8. It's always going to be unique. That one is tricky to prove. There's all sorts of ways to do it. My favorite way, so the fanciest way, so the fanciest method to prove uniqueness is to use something called the tensor product. But it's a bit more sophisticated. So I just mentioned this up, that if you're interested to kind of see uniqueness and you're familiar with something called the tensor product, you can try to maybe find it in some reference where that is done. Essentially, if you have 2 decompositions, you tensor it with something, and if you tensor it with something appropriately, you can cancel away a lot of the factors, and you can turn it into a vector space, and then everything becomes sort of easier from there. But we're not going to go there because this is not an algebra course. But I just want to mention the uniqueness theorem because it's very much related to the existence theorem that says that G decomposes in such a way. And what we will do is we'll just accept the uniqueness theorem, but the existence theorem that says that you can do this will actually follow from our discussion. So we'll show you how to actually do that. I want to mention a lemma, very simple lemma. And it's this, that if let's say you have a collection of generators, if these are generators for a abelian group G, then you can add, so you can multiply one of them by a negative sign. So if you multiply one of them by a negative sign, generate. So if these are generators, I'm not necessarily saying that these are free generators. I'm not necessarily saying that they form a basis, but just that they are generators for an abelian group. Then you can take them and you can negate them if you want to, right? Because that's sort of straightforward. The other thing is you can, of course, also, you can add a multiple of xi into xj as long as I is not equal to j. So what I mean is you can do this. You can take some multiple, let's say k times xi, you add it to xj, and then you keep everything exactly the same. So why does this work? Well, to keep the notation simpler, let's say we have 3 generators. Because, I mean, you'll get the idea if you just do it with 3. So you have 3 generators. Okay, let's keep it super simple. You have 3 generators. Let's take the first generator and add it to the third generator. So we'll use a certain multiple. So we'll have, let's say we have 4x1 plus x3. So we claim that these will be generators for the exact same group. So these 3 generate a group for you, right? They're generators of G. And we claim these are generators for a group. So the way you do it is you say, let's suppose these generate something. call it G prime, and you're going to show that G and G prime are equal to each other. Well, it's clear that G prime is contained in G because you can see x1 is already in here, x2 is already in here, and this element, well, this element is a combination of these three. So this element over here can be generated using x1 and x3. So that would mean that whatever elements you generate using these three, that these three is contained in G. Now you need to argue the other way around. Now to argue the other way around, it is clear that x1 and x2 are already in G prime. So you just have to show, so it remains to show that x3 is in G prime. And it clearly is for the following reason, because x3 can be written as, you're going to take x1, you're going to take the first generator in G prime, you're going to multiply it by -4, and you're going to add to it 4x1 plus x3. You're going to add to it, and then what happens in the end, well, what happens in the end is that you get x3. So you can express x3 by using those three elements. So it's actually important that you're adding a multiple into a different generator. If you add it into the same generator, then you would not be able to do it, because if you're adding the generator, so this will give you the same, this will generate the same elements, but if you were to, let's say, multiply the first one, if you were to multiply the first one by 4, then you're not able to express x1 anymore in terms of these three, right? Because you're not allowed to divide by 4. You're only working with integers here. It would make no sense to divide by 4. The 4 is just supposed to represent that you're adding x1 4 times. So how do you recover x1? How do you eliminate x1? You will not be able to express x1 using these three. That's why it's important that when you're adding, you see, that's what we're saying, you can add a multiple of x1 into xj, but they have to come from different positions. So as long as they come from different positions, that's okay to do it. Now, if you look at that, you say, that seems to resemble row operations on the matrix, and that's exactly how you do this. I mean, this is how it's related to linear algebra. So let me give you an example. Suppose G is an abelian group. Okay, suppose G has the following presentation, is an abelian group with the following presentation. So the presentation here would be this. Let's say you have two generators, x and y, and the relations that are being satisfied by those generators is quite simply x plus 2y plus 3z. Actually, yeah, let's make it 3 generators. Let's make it harder. Let's say we have 3 generators. So it's a group that has 3 generators, and then you have 4x plus 5y plus 6z is 0. So this is the presentation of the group. So what you know about the group is it's an abelian group, so we know what that means. It has 3 generators, it's generated by 3, and it satisfies this. What can we say about this group? So that's the group presentation. So that's what we call the group presentation. If you want to think of it more abstractly, so here's like a more abstract way. More abstract way of defining G. Not because it helps with solving the problem, but because it just nicely reinforces a lot of the concepts we've been talking about previously. So this is just a quick review. So I want to just show you how you can define G through universal property. So you can say that G has the following property, the following universal property, that if H is any other abelian group, and you pick target vectors, I'm going to call them vectors in quotation marks. So if you pick target vectors A, B, C in H, which satisfy the properties that a plus 2b plus 3c is 0, and 4a plus 5b plus 6c is 0, then there is a unique homomorphism from G into H, which sends the generators to the target vectors, so that f of x is A, f of y is B, f of z is C. So that's like a more abstract way of saying what this group G is without really saying what it is. That's like the universal mapping property that it satisfies. But it doesn't really help you find it. The question is, how do you actually classify what this group is? And the way you do it is you're going to describe, you're going to basically, I mean, if you want, you can kind of write it in matrix form. You can write it as 1, 2, 3, 4, 5, 6. This is supposed to represent sort of the first relationship, 1x, 2y, 3z is equal to 0. And then this relationship is going to be represented by 4x plus 5y plus 6z. And we're going to perform, so we will perform, we can change the presentation. We can change, well, we can keep the group the same. We can keep the group the same, but make the presentation look different. So the following operations will not change the group, but they make the presentation look different. So you can interchange rows and columns. Now this is a little bit different from linear algebra, because in linear algebra you do not interchange columns, you only interchange rows, because the rows correspond to equations. Whereas here, the columns represent to the generators. So if you're interchanging columns, all you're doing is you're just interchanging the way you're writing these. So it's still the same group, right? I mean, it does not matter what order you write these in. So the columns represent the generators, the rows represent the equations. The equations can be put in any order you want, so you can kind of interchange them, and the columns can be interchanged. So a little bit different from linear algebra is here you can actually interchange columns. You can multiply a row and column by -1 if you want to. You can multiply by -1. So, but you see, in linear algebra, you're allowed to multiply a row by a non-zero number, whereas here you're not allowed to multiply it by a non-zero number. So you're not allowed to divide by 2. That would make no sense. So here the only multiplicative operation is +1 or -1 multiplications. And then you can add a row or column into, you can add a multiple of a row or column into another row or column. So you can add a multiple of the first row into the second row, or a multiple of the first row of the second row into the first row, or a multiple of the first column into the third column, and things like that. That's what you can do. You can do this because that's what we were saying earlier, that I'm going to remove this. This is not necessary anymore. We have this way of representing it. You can do this for the simple reason because when we talked about generators, that's what we remarked, that you can change the generating set while keeping the same. You can change the generators while still generating the exact same group. So that's really what we're doing here. And now you basically use, and now you use row reduction to make this be diagonal. However, you have to be careful here. The diagonal will not necessarily consist of the number 1. The simple reason for this is because the way you make the numbers equal to 1 is by division. Here you're not allowed to divide. So here's how you can do it. 1, 4, 2, 3, 5, 6. So you already have a 1 over here. That's what they often call the pivot. And then you can use the pivot to create a 0 here. So what's the operation that we're going to go here? We're going to take like row 1. We're going to multiply it by -4. We add it to row 2, and then we substitute that into row 2. So let me just write down what these numbers are. So row 1 multiplied by, so it's -4, -8, -12. And now if you do the operation, you've changed the presentation of the group. So this is 1, 0, 2, 3, -3, -6. So what is this supposed to represent? This is supposed to represent the group X, Y, Z with the relations x plus 2y plus 3z is 0, and then this is 0x minus 3y minus 6z is 0. So that's really what you're saying. You are changing the relation. You're replacing the relation by this. And we remarked, in the end, it looks different from the original presentation, but you're still describing the exact same group. Okay. Now this makes it a little bit easier because you eliminated one of them, and then you work from here. Now I know that you're probably tempted to sort of like divide by -3 or something like that, but you have to not do that. You have to stay away from doing that. That's not an allowable operation. So what do we do here? Well, let me just check if I got the numbers correct. 0, -3, -6. So we have a 0. You can make a 0 over here. I know that normally you make this number a 1, right? Normally that's what you do. You turn that number into a 1. That's what we usually do. But here you're not allowed to divide. So you can get rid of the negative sign, but more importantly is you have a number here, you have a number here. How do you get a diagonal? You have a 0 and you have a 0. How do you turn that into a 0? Usually the way you do it in a linear algebra class, you make that a 1 and then you use that 1 to eliminate it. But here you are allowed to work with rows and columns. So you can add a multiple of a column to the other. So here you can use the first column to eliminate that number. So the operation that you're going to do here is you're going to take column 1 multiplied by 2, actually by -2, and you're going to add it to column 2, and you're going to substitute that into column 2. And when we do that, we end up with, so let me just write out what the numbers are. Column 1 by -2, so 1 times -2, so this is -2, this is 0. Now if you add those numbers, you have 1, 0, 0, -3, 3, -6, like this. Okay, then you can of course get rid of the negative in the second row. So you can go like this. So this would be 1, 0, 0, 3, 3, 6. Again, if you're tempted to divide by 3, you're going to have a problem. You're going to see it's going to lead to an incorrect answer, actually. So you have to keep it there because it's just not an allowable operation. You can only use those operations. So now you have 1, 0, 0 something. It's a diagonal, except it's not equal to 1. And now you're going to eliminate these two numbers. So how does one eliminate these two numbers? So the way you're going to do this is, so here's how you eliminate these numbers. You can eliminate this 3 very easily by doing this. You would take column 1. So I'll write it over here. So we're going to eliminate that 3. We're going to eliminate this 3. So we'll take column 1. We'll multiply it by -3. We'll add it to column 3, and then we'll substitute it into column 3. So by doing that, multiply these by -3. So this is -3. This is 0. So by adding these in, this is 0. This is 0. I'm sorry, that's not 0. That's 6. So that would give us 1, 0, 0, 3, 0, 6. And now we eliminate the 6. Now we're going to eliminate the 6. And the way we eliminate the 6, notice 6 is 2 multiples of 3. And that would actually be the problem. If we just divided everything by 3, we would be left with 1 and 2. We would be left with 1, not with a 3. So you'll actually end up getting the wrong answer in the end. So just because you could divide, just because they have common factors, does not mean you're allowed to. So let's see how we can eliminate it. So here what we do is we write this as C1, not C1. This is going to be C2, column 2, multiplied by -2. We'll add it to column 3, and then we'll substitute that into column 3. So multiply these by -2, so we will have 0 here, -6 here. And when we do the calculations, we end up with 1, 0, 0, 3, 0, 0. And now when it's written like this, this is fully simplified. This is fully simplified. It's fully simplified because it's a diagonal. It's a diagonal and everything else is filled with zeros. You can always do this, right? It's just like row reduction in linear algebra, except you go across rows and columns. It's essentially the same process, but you cannot get rid of this 3. So what does this mean? So what's the meaning of this? So this is a group. This is the group with the following presentation. So here's the presentation of that group. It's going to be, so you have 3 generators, X, Y, Z. the X generator has the condition. So this is X, Y, and Z. So 1X, 0Y, 0Z. So you're saying X is 0. Okay, so this just means this generator was the identity element. So you can forget about it. You can eliminate it. Okay, this one is saying that 3Y is equal to 0. And there's no condition on Z, right? There's no condition on Z. So what does this mean? This means, so X is just the identity element, and Y is a generator. Y is just the identity element. Well, actually, let me do this. I think you're going to find this easier. I think this will make it easier for you. So this is going to fit very, very nicely with what we said before. Now we use the product presentation. The presentation for a product. But what's the presentation for a product? The way the presentation works for a product is, this is what we talked about previously in the last class. How do you present a product of two groups? You take the two presentations and you put them together and you introduce commutative relations between the generators. So as a presentation for the product, this would be X is equal to 0. I'm going to split each of these separately. X, where X is 0. This is Y, where 3Y is 0. And this is Z with an empty, with no relation at all. So you split it like this. Generally, when you talk about the product, the presentation for a product, you have to introduce commutative relations between the generators. So, for example, let me just do it very, very quickly for you. Let's say G1 was the group that was presented as X and Y with no extra presentations and this is the free group of rank 2. Okay, this is a free group of rank 2. And G2 was another group. Maybe it would be better to call it X1 and X2. Yeah, let's call it X1 and X2. And this was Y1 and Y2. This is another free group of rank 2. Okay, so we're not talking about commutative groups here. At the moment, I want to not talk about commutative groups, just to use the material from last lecture. The way you find the coproduct, so the coproduct between these two, it's like a disjoint union. You just put these together, and you also copy and paste the relations. There's no relations here, so you do not write them down. So it would just be this. So this is the free group of rank 4. This is a free group of rank 4. But if you want to find the product between them, the way you would do it is, it's like a coproduct. This is the free product. Free product in the sense you do not introduce any extra relations. But with the product, you're going to copy these down. So you're going to have X1, X2, Y1, Y2. And then you have to introduce the commutative relationships. You're going to say that these two have to commute with those two. So you would say that X1 commutes with Y1. You would have to say that X1 commutes with Y2. But maybe I should just say it like this, that Xi, I'll write it like this, that Xi, Yj is supposed to be Yj, Xi. So you have 4 relations that are being introduced. The relations that are being introduced are, we're not saying that Y1 commutes with Y2, we're saying that those ones commute with those ones. So that's the way you would get the product, the presentation for the product. So it'll be a little bit different. Now, because this group is commutative, and we're only working with commutative groups in this discussion, there's no reason for you to introduce the commutative relations, because we are assuming that this presentation is a presentation for a commutative group. So you're going to just split it like this. And when you split it like this, you can now classify what this group is. This, when it's just a single symbol by itself with absolutely no relation, that's just a free group on a single symbol. So this is isomorphic with Z. Now, what about this? Here you're saying you have one generator, but that generator, when you add it 3 times, it gives you 0. That is the group Z mod 3Z. That's what it's isomorphic to. And this group, well, this is just a trivial group. This is just a group that consists of just 0 or something. It's just a group that consists of 0. So you can drop it out. This is sort of like the identity. You can drop it out. It looks a little bit funny. I know that usually when something is 0 in a product, it means the product is 0. But here, if you just think of the Cartesian product, if you take a Cartesian product with just a single element, you're getting the same set back, so it does not do anything. So you can kind of throw it away. So the group, so the final answer is that our group is therefore isomorphic to one copy of the integers and then mod 3. That's what we get. It's one copy of the integers and one copy mod 3. So that's what we've shown. So what we're doing here, this procedure that we're doing here, so it's clear how this process works. You're doing some kind of algorithm. There's some kind of algorithm. You can write a computer program for doing this, but there's some kind of algorithm that transforms this into this. There's an algorithm for transforming one into the other. And so this is called, this has a name to it. This is called the Smith normal form of an integer matrix. It has to be an integer matrix, and this kind of calculation, when you do it, it gives you something called the Smith normal form of a matrix. When you make it a diagonal matrix with zeros everywhere else by using row and column operations at the same time. And there's a calculator that does it for you online that I was able to find. You can do it using MATLAB. There's a code in MATLAB. There's a program. Like if you happen to have access to MATLAB, you can do this. It will do it for you. But you cannot do this using Wolfram, surprisingly. The simple reason is because no one written the code for doing it. But if someone was to write the code, then you can make Wolfram do it. But Wolfram online, when you use it online, it does not find for you the Smith normal form. Instead, it displays for you how many people in the United States have last name equal to Smith, and it gives you some kind of chart of how that name varied throughout the year. So that's what it does for you when you ask it to find the Smith normal form of a matrix. That's what it does. But here's a calculator that if you just search for it, I'll show you the site so you can see for yourself. So it says over here, finding the Smith canonical form of an integer matrix. So if you search for that, the matrix can be entered as a string of integers separated by spaces. So m over here, you see m by n, that's the number of rows. So we had 2 rows, we had 3 columns, and then here we'll write down. So we have to input it as a string of integers from left to right going down. So it was 1, 2, 3 in the first row, and 4, 5, 6 in the second row. So this is the way we're supposed to display the matrix, and then we specify the dimensions. And then if we do the calculator, you can see this is what we get. So that would be the Smith normal form of the matrix, 1, 3. So we get that. Okay, this is what we're getting. And then you can play around with it. You can make this be more complicated. Let's say this is a 3 by 3 matrix, and you just like randomly make up some numbers. You just randomly make up a bunch of numbers. And then you can see if you can do the calculation yourself. So 3 by 3 matrix. So that would mean 3 generators and 3 relations on the generators, and then you end up getting something like this. Now, what does this mean, by the way, 1, 1, 103? So let's just explain, if you get something like that, what the interpretation is. So if you were to get, let's say you use the Smith normal form, and you end up getting 1, 0, 0, 0, 1, 0, 0, 0, 103, then based on the same kind of idea, you're saying that 2 of the generators, these were trivial, they're redundant, and so the group in the end is just isomorphic to the generator where 103z is equal to 0. So you're just saying the group is 103z. So it's a finite group. So that's actually the presentation of a finite group, and the group is isomorphic to this. So that's what that would mean. Now, the way you get an infinite group is when you have zeros in there. So if let's say you had 2, 0, 0, 0, 0, 5, 0, okay, and then you had 0, 0, 0. So let's actually say you had this. So let's say you had something like this. Then this comes down to the group would be isomorphic to z mod 2z times z mod 5z. And then if the generators were x1, so we had, yeah, maybe I should add like another row of zeros maybe. It does not have to be a square matrix, but let's just add, we have, no, actually, yeah. So This is fine. No, this is fine. We have 4 columns, so we have 4 generators, and then the other 3 generators, x3 and x4, there's no relations on them, right? They're missing. There's no relations. So then that would just mean that our group would then be isomorphic to this. So that would be the way you would do it. Okay, so it's fairly straightforward to do. It's a nice algorithm. It kind of tells you how to solve the word problem for commutative groups. That's nice to know. Cannot necessarily do something like this for groups in general, because it specifically works that the group is commutative, that you can put the x's on one side, the y's on another side. You can move them around in a convenient way. And if a group is not commutative, you cannot do something like that. Now, I want to mention some comment. Here's a comment. What if you had the representation matrix, well, the relation matrix. So let's say your relation matrix looks something like this. This is just a small comment I want to say. So let's say you had 6 and 8. You have a bunch of other numbers here, which we're not interested in. You had 6 and 8. And you want to do something with this. Well, so what you need to notice is you cannot eliminate 8, because 8's not divisible by 6. And you cannot eliminate 6, because 6 is not divisible by 8. So how do you get a 0? You have to look at the common factor. You have to use something called the greatest common divisor. So the greatest common divisor between 6 and 8 is 2. That's the greatest common divisor. So you can therefore get the greatest common divisor by adding multiples. So here it's very easy to get. You would just subtract 6 away from here. So 8 minus 6, that would give you 2. That would give you 2. And of course, these numbers will change after you subtract them away. So these numbers will change, but that's how the representation matrix will change. And then, because 6 is now divisible by 2, you can remove it. So you can multiply the second row by -3 and add it in here. That will turn to 0. All of these numbers will change, but the presentation of the matrix, like the group, the presentation will change, but the group will not. And now you have this. Now you've produced a 2. So the point is, you do not necessarily produce a 1 like you do in linear algebra. Instead, you produce the greatest common divisor of the numbers. So those are the numbers that you get. Now, if the numbers get very, very, very big, you have to use, if the numbers get very large, then you need to use the Euclidean algorithm to find the GCD. So this is something you discuss in a number theory course. Here, it was very easy. You had 2 small numbers. The GCD was 2. You can just subtract one number away from the other and have it work out. But in general, it's much more complicated. You might have to take 15 multiples of one and 30 multiples of the other and properly subtract them together so that everything works out. So it's all about finding the GCD. Once you get the GCD, it's a common divisor for all of the numbers, and then you can use it to eliminate all of the other numbers. So that's basically the way that it works. It's the Euclidean algorithm that you have to use. So you have to be familiar with the Euclidean algorithm in order to make this work. Though the examples that I showed you, they were mostly straightforward, that it was clear. I intentionally wanted to use small numbers to show you how that works. So, this is the explanation for why that main theorem that we mentioned, that every presentation of a commutative group is a product of either copies of Z or integers mod n. Why does it work? Well, because when you use the Smith normal form, you end up getting some kind of numbers on the diagonal, like this. Everything else is just like a bunch of zeros everywhere else. So how many zeros you have down there, that's just going to indicate how many copies of Z you have. Those are like the free variables that you do not need. And then these over here, those are going to indicate for you what copies of integers mod n you will need, because that sort of tells you, like we've seen before, if this number is, let's say, 5, then that tells you you're going to have a Z mod 5Z. And then it's times whatever these are, and the ones with zeros, those will just be integers mod n. And in a way, it actually does kind of make sense, because what happens if you mod out by 0? So you do 0 mod 0Z. So you're just modding out by 0. So you're saying that 2 numbers, so then the equivalence relation would be that A is equivalent to B if and only if the difference between A and B and 0. So in other words, A and B are equal to each other. So it kind of makes sense also because if you have zeros down the diagonal, then the occurrences of zeros, if you mod out by 0, then this is just Z again. So the analogy even, also works even if you have zeros as well, if you interpret it in that kind of way. So that is basically the classification theorem for commutative groups. And the reason why I mention this is that if we are given two group presentations and we are asked to determine if they are isomorphic, the easiest thing you can try is to convert the group presentation into a commutative presentation. So for example, let's say I give you this group. I say it has 3 generators, and then you have x squared, y squared is 1, and then you're saying z cubed is xy squared. And then I give you another group, and this group has 2 generators, let's say a and b, and here you have a squared is equal to b cubed. And then I ask you, is G1 isomorphic to G2? Are these the same? Do these two presentations describe the same group, or are they different presentations? So this is not the perfect answer, but it's a good thing to try because it's the easiest, right? It's the easiest thing you can do. You can convert this into the abelian problem. So you would say that instead of x squared, y squared is equal to 1, you would instead turn this into 2x plus 2y is equal to 0. You would turn this into 3z minus x minus 2y is equal to 0. You would turn this into 2a minus 3b is equal to 0. Okay, you turn it into a commutative problem. And if these two groups were isomorphic as groups, then they would also be isomorphic as commutative groups with the same, when you turn those relations into commutative, with the commutative assumption. So you add commutativity to the presentations, and then you check if they're isomorphic. And if it was to turn out that these two groups are not isomorphic as commutative groups, which you can now check by using the isomorphism, but by using the classification theorem. So let's say it turns out that this one is isomorphic to, I'm making this up, I did not do the calculation, but let's say it ends up being isomorphic to z mod 3z, and this one ends up being isomorphic to 2 copies of z mod 3z, then you automatically know that these groups cannot be isomorphic because you can see there's a copy of 3z over here, there's a copy of z, and there's a copy of z, but there's this one extra copy of z here that the other one misses. And so by the classification theorem, this one is not isomorphic to G2 as a commutative group, and so these will not be isomorphic to each other as groups in general without the commutative assumption. So this is why I mention this, because the word problem of determining whether two presentations describe the same group is a very difficult problem to solve in general, but this is like the one thing that you can just turn it into a commutative problem and then see and then check from there if the two group presentations are isomorphic as commutative group presentations.